Hi, everybody. So in today's lecture, I'd like to talk about what happens in Gauss's law if you have a non-constant charge distribution. And yeah, let's get started with that. So what if your charge distribution is non-constant, but you still want to do Gauss's law? So we're going to use Gauss's law to find the electric field, but we're going to do it for a charge distribution that isn't something straightforward and constant, but for something which varies with the spatial coordinate. So here's the example problem that I'd like to do for this one. Let's say we have a sphere of charge and it has a radius A. Now the volume charge density of the sphere is not constant. Instead, the volume charge density is a function of the distance from the origin of the coordinate system or the center of the sphere. So in that case, we can write our volume charge density, rho of r, as b over r squared here, okay? Now, B is a constant, but as you can see, this volume charge density changes with respect to R. Okay, so we're going to find expressions for the electric field at all values of R using this expression for the volume charge density. So we're going to look at two separate cases, consider them independently, and then unite them to find the total electric field for all values of R. But the first case that we're going to consider is when R is less than A, where you're inside your sphere, and then when R is greater than A, when you're outside of your sphere. Now also, if the total charge on the sphere is big Q, so it has some total charge, like 1 microcoulomb or something, then using that total charge, we can solve for the constant B. Okay, so let me remind you of the steps for solving Gauss's law type problems. These are the way that I think of my Gauss's law questions every single time. So the first thing that I always do is I draw a sketch of the object and I choose a coordinate system and axes. When I say coordinate system, that may mean it's dictated by the charge density. If I've got a spherical charge, then I usually use spherical coordinates. If I have a charge that's a line or distributed along a cylinder, I use cylindrical coordinates. And then if I have something that's like a plane or a box, then oftentimes I use Cartesian coordinates, okay? I'm going to draw a sketch of what I think the electric field lines might look like. Now, I don't have to have it correct or perfect, but what I do want to make sure that I have right are the directions of the electric field lines at the points in question. All right, now based on my sketch for my electric field lines, I'm then going to choose a Gaussian surface. The rules of thumb for Gaussian surfaces are that the field lines have to be either parallel or perpendicular to the area vector for the surface at all points, okay? Now, remember also that the magnitude of the electric field has to be constant over your Gaussian surface. And this most often happens when you match the symmetry of your Gaussian surface to your real surface's symmetry. Students sometimes forget when they're dealing with Gauss's law that the Gaussian surface is imaginary. It's just something in your head to help you figure out what the electric field is like. It's not a real thing. Okay, not necessarily. Now, there might be some situations, some specific problems that are written so that the best choice for your imaginary Gaussian surface coincides with the real surface. But that's not always going to be the case. And most of the time, your Gaussian surfaces are only in your head. Okay? Now, the next step is once you've got your Gaussian surface chosen, now you can do the integral over the closed surface for the electric field dotted with your differential area vector. Remember that your surface, your area vector for your surface is going to change direction as you move over your surface. So for example, if it's a sphere, your Gaussian surface is a sphere, your area vector is going to point radially outward, okay? And that means that, for example, at some spots, your area vector might point in the plus y hat direction, and some spots in the plus x hat, because it's pointing radially outward, okay? So it varies, its direction varies. But the important thing is that it be either parallel or perpendicular to your electric field at all times, okay? And that means that the cosine theta, which comes from your dot product, will be easily evaluated to either 0 or 1. You don't want something complex for that dot product. You don't want an angular dependence that's going to vary as you integrate over your surface. If that's the case, if you can't think of a symmetry that does that, then what you really should do is not use Gauss's law and just do a direct integration of k dq over r squared for your electric field, okay? Now, once you've done that, once you've got that set up, then the deal is your electric field vector should pull out front, right? It should be a constant. And then it's just the electric field dotted with the evaluation of your area vector, right? And so basically then you're just integrating over the surface area of your object. Now, if you've memorized the surface areas for common shapes like cylinders, spheres, and boxes, then you can just plug that in. It's not even going to be that hard, right? Okay, now you can move on to your next step. You're going to solve for Q enclosed over epsilon naught. Q enclosed is the charge enclosed by your Gaussian surface, okay? So there's a few scenarios here. For one thing, you might be asked to solve for your field at some point where your Gaussian surface doesn't enclose any charge, okay? In that case, Q enclosed over epsilon naught is 0, and you'll most likely end up with a 0 field, right? Okay, fine, that's easy. Second is you're enclosing a charge, right? And you're enclosing all of the charge because you're outside of the real surface. In that case, Q encloses everything. No problem there too. Now, you also might enclose just part of the charge, okay? If you enclose just part of the charge, but you have a constant charge density, then you can just multiply your charge density times the volume or whatever that you're enclosing, okay? So for example, if you have a constant charge density rho, you just multiply rho times the volume that you're enclosing with that Gaussian surface, and then you have your enclosed charge, done and done. But today, what we're going to cover is the trickiest of all possible worlds. And that's that you're not enclosing all of the charge and your charge density is not constant. And what you have to do then is you have to integrate over your charge density, right? So that's what you have to do there. Now, once you solve for Q enclosed over epsilon naught and you solve for E dot dA integral over that, you just set those two things equal. You set left-hand side equal to right-hand side, and then it's some simple algebra to find the magnitude of your electric field. Once you've got your answer, you should always check to make sure it makes sense. Are the units right? Right? Step number one, if you've done something screwy, your units are wrong, your answer's wrong. Done and done. Also make sure that what's happening makes sense at the extrema. So for example, I often like to look at the case where something goes to 0 or something goes to plus or minus infinity and make sure that the answer matches what I think should be happening there, okay? All right, phew, that's what you should do for every Gauss's law problem. Now let's apply it to this specific example problem. And remind you what it is. We've got a sphere of radius A with a non-constant volume charge density, B over R squared, where B is a constant. We want to find the electric field everywhere. What do we do? Okay, so let's go. I'm going to stop my share here. I'm going to move to my trusty iPad here. Because heaven knows I don't want to write all these integrals out in an equation editor. What a pain that is. Okay, so let's do a sketch. First, I'm going to do the R less than A case. So here's my sphere. It's got a radius A. Okay. Now, I want to look at a value R less than A. Now, what would my electric field look like for this thing? Okay. Well, I'm not exactly sure how the magnitude would go maybe when I start this problem. Maybe I don't really know what the answer is in terms of the magnitude of the electric field. I don't have to, right? I just have to kind of know what direction it would point and what symmetries are at play. So let's say that I'm at some point here where R is less than A. And I'm going to sketch that right here. So here's R less than A. What would the electric field lines look like at that point? Well, I'm not really sure what magnitude they are, like I said. But I do know that this is enclosing a positive charge, right? It's a positive charge that is enclosing. And I know that what it's like for point charges is that the electric field points radially outward in all directions. So there's really no reason that it shouldn't do that for this too, right? I should have an electric field that's pointing radially outward everywhere. So even though I don't know exactly how the magnitude goes, I can at least draw my direction. Okay. Okay, so I've got my electric field sketched. Now I need to choose an origin. I need to choose a coordinate system and everything here. Well, it's pretty easy. If I'm dealing with spheres, I should really use spherical coordinates. Okay, so I'm going to use spherical coordinates here. And I'm going to choose a Gaussian surface that has its area, little differential area elements, parallel or perpendicular to the electric field that I've drawn at all points. Well, heck, if I draw a Gaussian surface that is itself a sphere, then that case will certainly be solved. Remember that what you most often want to do is match the Gaussian surface symmetry to your object symmetry. And if I do spheres, well, I've got a sphere, so that matches. So that's good to go. So my Gaussian surface is going to be this dashed line that I've drawn here, right? My area element is going to point perpendicular to the surface. So it's going to point parallel to my electric field lines at all points. So my electric field and my area will be parallel at all these points here. All right. Okay, good. So now that I've got my sketch done, what I want to do is evaluate the integral of the closed surface of E dot dA. Okay, well, there's no reason that if I choose the origin of my coordinate system as the center of the sphere right here, that the magnitude of my electric field would be different at the top or the bottom or the left or the right of my sphere. There's no reason. So it should be symmetric in all directions. So that means that I should be able to pull this outside of my surface area integral, my surface area integral like that. Okay, now my area element, dA, you have to remember your Calc 3 here and remember what the differential units are, your little dAs and dVs, your little volume and area differential units are for the various coordinate systems. So I've chosen spherical coordinates. So here, my dA, right? Well, it has to point perpendicular to the surface, which means that it's got to point radially outward, which is the r hat direction, okay? And then dA in spherical coordinates is r squared sine theta d theta d phi. That's from Calculus 3, okay? All right, now what I've got is I've got E dot dA is equal to, well, I don't know what my magnitude is. I'll just call it E, right? And then it's going to point radially outward, r hat. And then that's dotted with the direction of dA is in the r hat direction. And then I'm just performing the integral for my spherical coordinates of r squared sine theta d theta d phi, like that. Now r hat dot r hat is 1. So that's just E. And then I have the integral of 0 to 2 pi, 0 to pi. R squared isn't integrated over, it's an area integral. So that pulls out front r squared, right? And then I have the integral of sine theta d theta d phi. Okay? Now remember your spherical coordinates. If you have some vector r pointing outward, then the way that they go is phi is the angle that swings from the plus x-axis all the way around. It goes from 0 to 2 pi. And theta is the angle from the z-axis, and it goes from 0 to pi. So that's why the limits of integration are what they are in this integral right here. Okay, so I have the integral of E r squared times the integral from 0 to 2 pi of d phi times the integral of 0 to pi sine theta d theta. It's supposed to be a 2. I should make it look like a 2. Sorry. R squared. There. Okay, now the integral of d phi is phi. So this is E r squared times phi, evaluated from 0 to 2 pi. And then the integral of sine of theta is minus cosine of theta. And then you integrate that or evaluate that from 0 to pi. So phi integration there gives you 2 pi because it's 2 pi minus 0. And then you have minus of cosine pi minus cosine 0, which gives you 2. So this evaluates to 4 pi E r squared. There you go. All right, now I broke that out for you and did that integration over the angles one time. That's all you get in this lecture. From here on out, your angular integration, I'm just going to write down 4 pi. Okay, there you go. Okay, now let's talk about Q enclosed over epsilon naught, because that's really the tricky part of this integral. My volume charge density is not constant. So what I've got to actually do here is evaluate the integral of rho dV, and that will give me my enclosed charge. Now, depending on the problem, okay, here we've got r less than a case. So since we're solving for r less than a, then the limit of my integration is going to be what's contained by my Gaussian surface. Once I get to r greater than a, I would integrate not over my Gaussian surface, but over my real surface, because my Gaussian surface is bigger, okay? So you integrate over either your Gaussian surface or your real surface, whichever is smaller, okay? So here I'm going to integrate over my Gaussian surface because that one is smaller here. All right, so this is rho dV. dV for spherical coordinates is r squared sine theta dr d theta d phi from your Calc 3, okay? Now, since I'm calling my value of where I'm at r, then maybe to make things a little less confusing, I hope it makes it less confusing, instead of doing r squared and dr, I'm going to do r prime, and then we'll understand that that I'm integrating over r prime, and then my limit will be r. Does that make sense? Hope so. Pause me if it doesn't. So here we go, 1 over epsilon naught. And then I'm going to plug in for my formula for rho. And then it's a triple integral. Yay, Calc 3, right? And I'm going to integrate from 0 to r for my radius term. I've got 0 to pi for theta and 0 to 2 pi for phi. So then rho is v over r prime squared, right? That's rho. And then my dv is r prime squared dr prime sine theta d theta d phi. D phi's on the outside, right? The 0 to 2 pi limit. Okay, so I'm still integrating over 0 to 2 pi d phi and 0 to pi for sine theta d theta. Like I said, I'm not going to repeat that. So I'm just going to pull this out front. So let me pull everything out front that's a constant. B is a constant. So I'm going to have 4 pi now from my angular limits there. B is a constant and epsilon naught is a constant. Okay. Now all I'm left with is my integral for the radius. So I've got 0 to r, and then I have, look here, 1 over r prime squared times r prime squared, and the r primes cancel out, top and bottom. So that just leaves me dr prime, right? So if I integrate dr prime, I just get r prime, and then I evaluate r prime from 0 to r, and I get r. So that means that the evaluation of this integral, Q enclosed over epsilon naught, is 4 pi br over epsilon naught. There you go. All right. Okay, so I've solved for Q enclosed over epsilon naught, and I've solved for the integral around the closed surface of E dot dA. Now the next step is I just set those terms equal to one another and then solve algebraically for my electric field magnitude. So here we go. 4 pi r squared E, that's the left-hand side, which is the integral of E dot dA. And then I set that equal to Q enclosed over epsilon naught, which is 4 pi br over epsilon naught. Now I'm solving for the magnitude of my electric field. Okay, so my electric field is 4 pi br over epsilon naught times 1 over 4 pi r squared. You can see the 4 pi's cancel out top and bottom. The r up top cancels out one of the r's on the bottom. And I end up with the expression b over r epsilon naught. So that's what my electric field is like inside. That's the expression. Okay, now let's also do the next case for r greater than a. Okay, so I'm going to draw myself a picture. Here's my charge. Here's my radius. And now I'm interested at some point here, which is outside of my sphere, okay? Well, yet again, I don't really know what the magnitude is there, but I can tell you that it should point radially outward, right? Sorry, should point radially out. And so just like a point charge or the uniformly charged sphere, like we did before in a previous example, my Gaussian surface should match the surface of my actual charge distribution, which in this case is a sphere, okay? So I've got that going there. And just like before, now I've got my Gaussian surface chosen, and you can see that the area vector is parallel to the electric field vector at all points. So if I do my integral of E dot dA, then I get E dot the integral of dA. And honestly, it should be no different from before, right? My radius here is R, so I should get 4 pi R squared E, just like before. Nothing's really changed on the left-hand side, okay? What has changed is the right-hand side. So Q enclosed over epsilon naught. Okay, well, I said that if you wanted to figure out Q enclosed over epsilon naught for non-uniform charge densities, that you're going to integrate over the limit of either your Gaussian surface or your real surface, whichever is smaller. So in this case, my Gaussian surface is bigger than my real surface. Now, if I attempted to perform an integration over my Gaussian surface, I would be integrating over charge that wasn't there. So what I want to do now is I want to integrate over the limits of my real surface to figure out what charge is enclosed, okay? Don't want to integrate over my Gaussian surface anymore and go from 0 to R. I only want to integrate from 0 to A because that's where the charge is. Fine. So this is 1 over epsilon naught, integral of rho dV. Second verse, same as the first, right? I've got 1 over epsilon naught, okay? It's a triple integral. The limits over my angles are 0 to 2 pi and 0 to pi. But now I'm only integrating from 0 to A because R is greater than A at this point. So I've got B over R prime squared, and then times dB, R prime squared, dr prime, right? And then I have sine theta, d theta, and then d theta. Okay. So now, pull my constants out front. I have B over epsilon naught. My angular quantities integrate to give me 4 pi, just like before. Told you I wasn't going to do it again. Okay, my R prime squareds cancel out top and bottom again. And so I'm just integrating over dr prime, and I'm doing that integral from 0 to A. So I end up with 4 pi BA over epsilon naught. Now, I've actually accidentally solved part B here. I don't know if you remember, but part B said, you know, if the total charge enclosed is big Q, then find out an expression for B. Well, if I'm enclosing all my charge and all my charge is Q, then Q enclosed over epsilon naught is big Q, isn't it? Over epsilon naught. So that means that 4 pi BA is equal to big Q, and then B is equal to big Q over 4 pi A. So this is my part B answer. I kind of got it along the way. Okay. Okay, but let's continue on in our journey to solve for the electric field everywhere. So if we set the left-hand side equal to the right-hand side, the integral of E dot dA equals Q enclosed over epsilon naught, our expression for E dot dA was 4 pi R squared E. And then that's equal to big Q over epsilon naught, isn't it? Right? And big Q is over epsilon naught could also be written as, here we go, Q over, or 4 pi BA over epsilon naught. So either one of those expressions works here, okay? Because I've shown that big Q equals 4 pi VA. So I can write my electric field in either one of two ways, depending on what the problem wants. You might be asked to do something different, so I'm going to solve both. Put a little dashed line here to show you what I mean, okay? So here, I've just got big Q over 4 pi epsilon naught r squared, which is the Coulomb constant case of EQ over r squared. So that's it. It's the same as a point charge equation, and that makes total sense. The further away you get from a spherical charge distribution, the more it looks like a point charge, right? Now, I could also write it in terms of B. If I do that, it would be E is equal to 4 pi BA over epsilon naught times 1 over 4 pi r squared. The 4 pi's would cancel, right? And then I would end up with BA over epsilon naught r squared. So the electric field could interchangeably written in either of these two ways and still be correct here, okay? So that's my electric field. So I've done what the problem asked me to. Now let's go just a step further, right? Let's make some sketches of this stuff so that we can really conceptualize it. Okay, well, the first sketch I can do by hand. The sketch I want to draw here is what Q looks like as a function of R, okay? So let's draw this. On my vertical axis is Q as a function of R, and on my horizontal axis is my position R. Okay, well, remember that my Q enclosed was equal to 4 pi BR, like that, okay? Because remember, this comes from Q enclosed over epsilon naught was 4 pi BR over epsilon naught, which we solved for in the very first part of our question. So what this means is that the amount of charge that is enclosed grows linearly with R, with its distance from the center. So if I were to draw that, it would just look like this. Now, here is R equal to A, and at that point, it doesn't grow anymore, and you just have no more charge. So you could draw your charge distribution like this if you want to, like a step function, so that you can see that at R equal to A, it cuts off and there's no more charge after that. Okay, so that's Q of R. Okay, now let's look and think about what the electric field looks like as a function of R. Now to do that, I've got some Excel files pulled up here, just to make a better sketch than I can really do by hand, because it always looks clumsy when I do it by hand. So here, let me stop my share on my iPad and start the share here on my regular computer screen. And I'll drag my Excel file over, okay? Okay, so what I've done here to make Excel able to do all this stuff is I plugged in some numbers, okay? I called the total charge 1 microcoulomb, because why not? I called the radius of my charge distribution a centimeter, because I don't know, why not? And then if you solve for B, you get about 8 times 10 to the minus 6 in SI units for the value of B, okay? Now, in this column D right here, what I've done is I've written out the position from the origin or the center of that sphere in meters. So I start off, of course, at R is equal to 0, but then in steps there, I go in steps of a millimeter out from that, okay? All right, then I use the expressions that I found for the electric field in our analytical solution, and I solve for the electric field in this column E appropriately, right? Column E. Now you can see here that at 0.01, I'm at R equal to A, right? That's where my charge went. So I had one expression for going up to here and then a different expression for R greater than A for my electric field in my calculation. And you can see that here, that it's slightly different expressions for R less than and R greater than A. And I'll be happy to share this file with you on our course webpage. So this plot here, this one right here, this is for R less than A, and it goes up to the value of R at A. Now you can see that our electric field expression was proportional to 1 upon R times some constants. And so what happens with the electric field is that as R goes to 0, that expression will go to infinity, right? because you'd be dividing by 0 there on the bottom, and that goes to infinity. So I like to think of that as, if you think about what's happening with this volume charge distribution, it was proportional to 1 over r squared. It was proportional to that. So as r goes to 0, our charge density goes to infinity. And that's almost like being in the middle of a point charge, isn't it? Right? So you have this huge electric field there, and then it falls off like 1 upon r, okay, as you go out. So this is the electric field expression for going up to r equal to a. So it starts off really strong electric field near r equals 0, almost infinity really, right? And then as you increase value to the radius, it falls off like 1 upon r, okay? Now, the electric field magnitude for all values of r, here's the cutoff. Here's r equal to a at a centimeter, right? Or 0.01 meters. And if you stare hard enough, and if you play with the file, you can tell, there's a different sort of slope, right? You have a 1 upon r expression for the electric field up to 0.01. And then once you get past r is equal to a, it starts to fall off like 1 upon r squared. So you can see that there's a little discontinuity in the slope here at 0.01 if you stare hard enough. So that's what the electric field would look like. Once you get beyond that thing, it looks just like a point charge. It falls off like 1 upon r squared. Okay, I hope that was helpful. Let me know if you have any questions, and I'll see you in class.